So thank you very much. So I'm going to start in a strange place. So this is a picture of where I was born. I was born on a road job, which means two things this picture is to convey. One is that I'm old, and the other is that I have some building sensibility in my background. So I think in some ways, as a designer, I really think a lot about, or at least try to think a lot about building. So I'm also going to sort of go off course here a bit in terms of thinking about at least what I mean by adaptation. And for me, I got fascinated by this idea that really we could use evolutionary models to think about technology, and in particular to look at artifacts. And so this is the idea that maybe a bridge is an artifact, and look at how those artifacts evolved over time and what that means. And in the biotech space, obviously, they especially with genetic algorithms and actual genetics, they think a lot about how to do this in a slightly different way. This sensibility about a fitness landscape and climbing a mountain to get to higher fitness is at least a metaphor that I think we can adapt. And it's also about bridges of fitness. Is it doing its job, and is it useful? This is this idea of fitneity. And maybe this is the strangest part of what I'll have to say. So one is this idea that the mountain keeps moving, yeah, and so how well adapted if we're trying to climb the mountain and the mountain's moving out from under us, and there's also this sensibility about Rogers' paradox, and I'll use these words sort of interchangeably. But there's this idea, and the paradoxical part is this idea that there's some equilibrium. If the environment changes, and this is just an XY change in environment, and you have learners who are adapting to what that change is, and you have imitators. Yeah, okay, yeah, no worries. So this idea of so learners are you can think of interchangeably as innovators, and then imitators. It's a way of thinking about cultural transmission. In this sense, I think the cultural transmission part is really important. How do we choose good ideas and then reuse them? So I want to highlight where I've been both, I think, a bit of an innovator, but also a bit of an imitator, and I think both are equally important in some sense. And so I'll try to walk through that in a way that I hope makes sense. The other challenge for me is that we have these, this is not in this Stuart Kaufman's model, this is a sensibility about how the fitness component depends on multiple categories or multiple other components, right? So this is, if they're not independent, then you have this problem of figuring out which space you should be headed towards. And obviously, if the space is changing, it makes it even more complicated. I want to argue here that I see really two slowly changing landscapes that at least has been the focus of my career. And one is, and I'm talking, when I say slow, I'm talking 100 years, more than a generation. The length of the artifact, the service life of a bridge is the way I like to think about this. And so I would say 100 years ago or better, the thing that drove decision-making was primarily cost. Certainly not safety. We had many collapses per year with many deaths. Certainly not longevity. Many bridges lasted less than 10 years. Yeah. And environmental impact, I think, is not consequential at all at the time. And I say 1980s to present just because that's when I've been practicing. And so safety has obviously changed dramatically. Safety and cost, I think, are still the largest drivers. What's changing right at the moment is environmental impact or sustainability, however you want to think about that term. And so I'll focus quite a lot about safety and cost and how to get there. Now, for me, cost is underpinned in terms of what's changed and also slowly changing, is materials were the primary cost 100 years ago. And now they're not not even a third of the cost. And I've gotten agencies and even the steel manufacturing industry and the concrete industry to make numbers on this, and it's absolutely clear it's maybe one-third or less of the cost. And yet we still practice design by optimizing the use of materials. Now, some of that may feel strange as in regards to sustainability. It seems like less materials may be quite a bit better, but there are circumstances where it's not. At any rate, I spent a lot of my career not optimizing for materials, actually optimizing for the opposite of material costs. So that's been maybe an underpinning. And then it always bothered me. And so, speaking here and thinking about the Roman Point collapse and progressive collapse in buildings, and really I'm a product of September 11th in terms of my generation's practice. And yet these are all buildings, and we still, as of today, don't really have progressive collapse guidelines or disproportionate collapse, as you say here, in the U.S. practice. And it's funny because we've had exactly the same collapse history as we've had in buildings, what we've had in bridges. We've just somehow called it something different. And so when I started my practice, I really was concerned about why we don't have progressive collapse guidelines. Why are we designing bridges where we could have one component fail? And so now it comes to the sort of formative of the beginnings of my career, and some of this will seem a bit strange, I think. But this was a project in Boston where Christian Menn was the conceptual designer, and I was the engineer of record. And there's maybe two or three important takeaways for me, at least in this. One is the cable spacing was so tight that it was easy to tolerate the loss of a step, perhaps even the loss of two stays. And this was just a choice, right? So this cable spacing is maybe 6 meters, the tightest cable spacing of any major bridge I've ever designed. Yeah. It's a strange idea. Yeah. And then maybe the other piece, and this is quite a mess if you imagine, right? You have a cantilevered walk, this two carriageway cantilevered bit, and you have then much more force in these cables than these cables, yeah, which produces obviously a lateral force this way, which wants the bridge to go to the left, yeah, and it also wants to pull the tower over to the right, and in this case, twist the tower. So the one bit of cleverness here, I think, that no one will understand, yeah, except a bridge engineer, is just by moving these two cables just an inch or two this way balances the forces, the torsion in the tower, the lateral bending in the tower, and minimizes some of the lateral bending in the deck. Yes, so these subtle things I thought were fascinating, right? That you could play this game. And so since then, I think many cable stayed bridges have taken into account that just a subtle change where you're directing very large forces can create quite interesting opportunities to let's say, misbehave. But the real story here is what a mess this project is. So we were building this cable stayed bridge underneath an existing double deck structure, yeah, where the columns of the double deck structure went through the side spans, and you can see the cables. It's a little hard to see, but the cables extend underneath so that last cable almost hits. It's within 6 inches of hitting the existing girder. So this bridge had to be built, and then the double deck bridge removed. And so we had to build a hole for that column and remove the column later, and so on. To me, there's something fascinating about this being an early part of the work that I did as a practicing engineer. It's a little bit like trying to build an automobile in your closet. Yeah, it's just there's too much going on and not enough places to do it. But it also gave me a sensibility about how critical a construction strategy is and how it should be baked into the engineering. And a lot of what we changed, even in Menn's conceptual design, was to try to get this to work a bit better. And ultimately, I think it's a successful structure. But the other thing that it instilled in me, and this is something I didn't appreciate, was how much of forcing it took to install some of these components. And the cleverness of erection engineers in order to build this bridge was far more clever than anything we did in the design. And that's something that stuck with me, is that I really had to be a better structural engineer. I had to understand erection engineering in a deeper way and really start to integrate the erection strategy into the design. It's a theme that I'll come back to. So the other piece was one of safety. So people would probably not recognize this, but only in the US would we say tied arches are not permitted. So in 1978, we had some problems with some welded tied arches, and the federal government said, "Thou shalt not build tied arches." Yeah. And so I sort of grew up in that "thou shalt not build tied arches" sensibility, and yet this particular crossing of the Ohio River really wanted to be an arch in many ways. It could have been a cable-stayed bridge, but for reasons that are historic, this island here really couldn't be touched. Yeah, and so building a backspan over the island and having construction works over the island was really to be avoided. So an arch was the natural solution, and then I had quite a time convincing the federal government that I could make an arch safe enough. And what that entailed is two steps here. One was using this inclined cables that cross twice, and the other is a bolted up box. Yeah, so the tie could tolerate fracture if any one of the components fractured. So this is a little bit back to the future, you could say. We're going back to bolted connections. And in my view, I really do wonder if we left bolted connections too soon. Yeah, when we went to everything welded, and all of the problems that happened in the 70s with tied arch bridges had to do with welded structures. So you get the idea. I was trying to get a new conceptual mechanism, and this was not, but at the time, no one felt that this would be redundant enough. And the argument I made was that it's not just that I can tolerate the loss of any plate, but I could tolerate the loss of a plate and still maintain full live load capacity. And the only way to do that is with, so losing this plate, or losing a flange, or losing the web, the only way you can do that is with cross cables with a network arch. And so then I got very interested in the dynamics of cable loss. Obviously, that was something we worried about in the bridge in Boston. It was amazing to me how an arch bridge with cross cables can tolerate the loss of not just one, but multiple cables. And so this also, I think, had a profound influence on my sensibility about design. And then, not for nothing, you look at the comparisons for under live load, for example, and it's just dramatic. You have a system that is 10 times more efficient, whether it's displacements or moments. And you wonder, for me at least, I wonder, how did we not find this system earlier? And why were we ever designing bridges, arch bridges with vertical hangers? And so, of course, it was found earlier, and I didn't realize this at the time, but Per Tveit, this little-known Norwegian, and he ended up as a professor, but he built two bridges. The backstory on this is cute. His mom knew the Secretary of Transportation in Norway, and she said, "My son's got his PhD on these things that make no sense to me. You should let him do one." And I guess in Norway, they said yes, and so he did two. He said there was actually two network arches that he did, and then he became a professor and didn't do much about network arches for 30 or 40 years. And then he called me when he saw Blender House. He said, "Well, how did you find my stuff?" And I said, "I didn't know your stuff existed." Yeah, and he said, "Well, what were you?" Because his argument was for slenderness. Yeah, that you can make these very, very slender, and these bridges are extremely slender. And I was making exactly the opposite argument about safety. But one other theme, and this goes back to really the appreciation for the erection engineering. The engineer, and so this is another problem I have with arches that I'll come back to over and over again in my career. They're held to build, and the engineer who did the erection engineering for this arch, and so he designed everything, all of the temporary stays, all of these jackable struts. The guy was an absolute genius. You would never, in talking with him, you would never knew how much he knew about arches, but it was absolutely fascinating to me. But what's always bothered me is you look at all of this temporary structures, yeah, And this I think of as lost dollars. These are dollars that don't go into the final structure. They go into getting the final structure there. And when we think and talk some about sustainability, I don't think we measure these things clearly enough. And so, yeah, these I think are formative for me. So then my argument here, it's a very simple one, and there's a few of my students, former students in the room who've heard me say this, but for me, it's just optimizing for fabrication, transportation, and erection with very little thought to material optimization. And so then I went on a little bit of a spree of taking over budget pedestrian bridges and redesigning them for roughly half their cost. Yeah, so this is another thing that I think surprises people, that design can mean 50% reduction in cost. Yeah. And so these are examples of those three that I'll go through quickly. One's a sort of strange idea about a curved cable stayed bridge, an S-curved cable stayed bridge. Maybe that's not so strange, but I think in the way we achieved it. So, of course, this was a design build project, and this was one that used the model of we have $22 million to spend, give us the best bridge you can. And so we were able to give them the bridge that was bid at 47 million. We gave them exactly the same alignment, a very similar bridge, but some fundamental differences that I'll get into. But the fabricator and the contractor that were working, the contractor had never built a cable stayed bridge, and the fabricator said, I will not do a curved bridge. So the beauty here is there's not a single curved member anywhere on this bridge. And then a bit about how we saved so much money. So the original design had a single cell box, asymmetric cable arrangement, inclined towers, and even in the middle of the country, this is in Omaha, Nebraska, wind governed, and we were able to use a much less, I would say, a section that has much more drag, but is obviously much less deep. And so we were able to, just in the foundations alone, we saved half of the cost. And ultimately, this bridge was delivered very successfully. But I come back to the no curved part, and now you'll see the sensibility about erection. So for me, I wanted every one of these pieces to be exactly the same, and also for there to be no stick framing. Yeah, it's a strange idea, right? That piece has to be the same piece, and there can't be any little pieces to pick up. Little pieces to pick up is hook time. Yeah, it takes a crane operator to pick something that he shouldn't need to pick up. So for me, I started really thinking about, well, how do I make a piece that's erectable? Yeah. And then if that piece is exactly the same, so this is a pie slicing plan, if that piece is exactly the same, then every single one is the same. Yeah. And then this becomes, and so the fabricator was very happy to do this. And it was done very cost effectively. The other piece of this, and Verlinger and I had a little discussion. He taught one of my classes. We had a little discussion, and I think he wasn't convinced. My argument on curved bridges is the tower belongs in the CG of the section. Yeah, it's absolutely the only place where and then the tower can be vertical and it behaves just like a tower should. And if you incline the tower, you immediately get to a much more complicated set of circumstances. And then the other thing, of course, is that this wants to close right? It wants to close the curve. Well, the curve, it's easy to build the curve at a bigger diameter, right? So and this is a little bit like the Zakum problem all over again, right? You can pre-build the banana slightly wider than it needs to be, and it ends up in the right place. But the real advantage in all of this with a vertical tower and quite a simple construction of the foundation, so no cofferdams, a single drill shaft. That's really what saves the vast majority of the money. So then another one is this is sort of a classical problem of a bridge over an interstate. In the U.S., we found nice communities, and then we built 8-lane divided highways through those communities. And so the neighborhood is here, the high school is here, right? And so instead of having a bridge, and even the abutments were built for this, but the bridge was never built. And so the head of the Department of Public Works had been trying to get this project done for its entire career. And so the bridge was designed all in concrete, and it was twice the budget. And so the project had to be canceled. He flew out and met with Les Robertson, one of the guys on the wall, and and said, I want your ideas on how to do this, but I only have this much money. And so we redesigned this in steel in 6 weeks, and it has some features that I think are important. One is that the tower is built in halves. The tower legs are built in halves, so there's only two connections at the top and at mid height. But the CG of the space plate is so that the tower is freestanding vertical, if that makes sense. And the other piece is that tower fits on one truck. This is the idea for me, transportability. So the concrete tower took, the schedule was 2 months to erect. This took 2 hours. Yeah. So you get the idea. More expensive materials, in a sense, maybe more fabrication done off-site, but this is the sort of thing you can do. And for me, it's a sort of funny thing, right? And this is a high seismic region, right? So also the connections happen in places where there's very little movement. Yeah. So I'm also not worried much about that. But that's not the whole story. The whole story is then, it turns out in this divided highway, there were places where I could drop false work on the top of barriers. And so the bridge, these pieces are all the same. They're erected to span from false work to false work without the cables. Yeah. And then it's built high and the cables are installed unloaded. Yeah. So this is something I also wonder why we never did, right? If I'm going to install in false work, just install things high so it's easy to install the cables and then let it go. Yeah, and this is exactly the way it was done. And when projects like this are successful, like there's the Department of Public Works is putting the last cable in, so this is one that, and the entire bridge was complete with about 80 hours of hook time. So you could only work at night for 4 hours. So that was really, it was only 20 nights to erect the bridge in its entirety. And so the last one here is even stranger still, and this has something to do with the fabrication piece. So this was an over budget project, and the idea was that this is to a zoo for very young children, and the bridge in the redevelopment of the zoo was called the Bent Bridge. So I sort of took that on as inspiration, and the idea here was, could I make an arch bridge out of one? Actually 2 rolled sections. And so here, this is obviously core 10 steel, so you don't have to paint. This is a perfect place to use core 10 steel in the middle of California. But the challenge here is you can't get core 10 steel, you can't go to the store and get core 10 rolled sections. So you had to have a minimum order. The minimum order was 20 tons. So I got 20 tons of steel in these 2 rolled sections. And so strangely, and I think there's some strangeness about this bridge, is that obviously everything's bent, but these are W1876, so 18-inch T beams cut in half and bent. This is the arch ribs is a W14 by 120. That's it. Yeah. So you go to the fabricator and order 2 pieces of steel, and the tie girder is actually the same WT. Yeah. So in a sense, for me, it's a strange operation, but a very successful project. So these 2 arch bridges built for less than $3 million. And they're quite slender. I think they have some aspects, and this is where also I'm partial to no railings in these circumstances. So the railing is a little bit hard to see, but there's just a cable and a mesh. And the railing is eliminated. Railings, it turns out, in pedestrian bridges, I've done some where the railing costs more than the bridge does. It's preposterous, yeah. So I'm very interested in ways of. So part of the reason for close cable spacing was to eliminate the expensive railings. So now we'll go completely another direction, because I think oftentimes we get up here and talk about long bridges and these sort of iconic projects, and in my view, many of these other sorts of projects are much harder, and in this case, I think much less safe. So this is a little bit about how unsafe the construction can be. So the story here is that this is a 2-track bridge. Okay, we have to maintain train traffic on one of the tracks while we replace the other track all next to live traffic. Yeah. So, this is one where something goes wrong and everybody dies. The 1,000 people in the train die and they fall onto the 1,000 people in their cars. And you can imagine, right? So this is one of these circumstances where it's really probably the riskiest project I've ever done. And I know this is being recorded, but my firm was probably not paying as much attention as they should have when we pursued this project. So this was also a design build project where you sometimes have less control. So the story here was that what we came up with, which I think in many ways is not ideal, was ideal from an erection perspective. So the owner expected that we would do 2 spans a weekend. So this is all in a 55-hour, I should have said that, it's all in a 55-hour weekend outage. Yeah, so you have to have the rail back up, and so 2 trains are going in both directions back in rush hour. So they were very complicated spans, and the idea was that we would do 2 spans a weekend. And with the system we came up, which is really the system that I'll explain in just a second, we were able to do 10 spans a weekend. And so you imagine every weekend was your risk. We had 5 times less weekends, less risk than anything else what we did. And this is another thing I think about, even in terms of sustainability or how we think about the work that we do. Maybe the time where we're unsafe is really important and consequential. And so this is we did have daylight, and we tried to get as much done as possible in daylight. And this is where the spans are really ready to go. But most of this was done at night, and this was Kiewit, who just did a fantastic job. And so just to describe the system, so these are in-span hinges, what you would never do, I think. Yeah, but they're in a circumstance where we're relying on the flexural capacity of the columns. And this was actually not in the design. In the design, we were supposed to retain the columns. And the argument I made, which is I'd much rather make this splice than this connection to existing. Yeah? And so that was the other piece that made all the difference. The other part that we didn't know about until we really got into the job is that these are pinned at the base in any case. So really unstacked. This is all the early 1900s structure. And so this sensibility about building quickly and safely, I think also, it's not so much the final structure, it's getting the final structure there that was the risk. And then with this idea of constructability first, this is probably the first bridge I designed around a crane. Yeah, so this is a nasty New York problem. They couldn't figure out how to do it. When we interviewed for the job, I said, if you don't do it this way, I'm not interested. Hire somebody else. And the problem here is that we're replacing this section of viaduct. Yeah, but between houses. There's no way in, no way out. It turns out this is an elevated structure with low clearance, and that's an elevated structure with I couldn't even get a normal sized crane in. Yeah, only in New York. Yeah, you have maybe 4 meters clearance, and that's it. And so the logic for me was that we should use a pick and carry crane. And I thought for the life of me that there's no way they would have built this originally like this. It's just too silly. But in fact, they did. And that's why this stretch between the 2 buildings was all built in concrete, yeah, which was a nightmare to get out, and there was no reason to put concrete back in, and I'll get into why. The other piece was that it was right next to, when I say right next to buildings, commercial buildings and houses that were active, it was right there. And then, of course, we have all the power and systems that we had to support temporarily, and even just the little mini suspension bridge we had to build to support the cables, because we're still operating the trains that are connected. We're dropping out this section, and the trains are still operational. So you get the fun. So then designing around a crane. So these are cranes that were developed for tunneling. And the reason they are useful in tunnels is they're short, and they can pick loads up and carry them. So these are pick and carry cranes. You can spin the load around. Yeah, and so these are hydraulic telecrawlers. Before these existed, I don't think we could do this job. So this you can pick up, you can drive under the bridge because it's only 3.5 meters tall. You can drive under the bridge, extend the tracks, pick the load up, carry it around. And so in terms of cross section, this is also a stupid cross section. Yeah, you don't for a two-track bridge, you don't put a mid-span splice in the floor beam yet. It's just nonsense. But in terms of making the pieces over the road transportable, it's brilliant. Yeah, so all of these were brought in. In New York, there's no place to store anything. So these were brought in live. Yeah, so as we were setting pieces, you bring them in, pick them up, carry them in. And when I say carry them in, I mean carry them in. You have to pick up with a crane, drive them into their funnel, and then work your way out. So you have to work your way in to demolish and work your way out to construct. And so then there's many of these projects that are just constrained that nobody thinks about that make no sense. But this is a cable stayed bridge in Texas, and you can see this is the light rail tunnel. And the light rail people had no interest in any surcharge loads to the tunnel whatsoever. So we have these sort of fishing poles, that are cantilevered out just to support the structure. And then the beauty of this as a system is each piece is sort of self-supporting. So that bit is you can actually pick up each piece independently and then connect them together. So in terms of construction, quite effective. There's the sort of end product. It's bizarre a bit, I think, but it's interesting. And then you can see, maybe I've taken redundancy to a logical conclusion, but we were trying to use all the same cable. Yeah. So this is another thing that I think we don't do enough, like efficiency. Yeah. Why would I have different cables? I just used the same cables, and I needed 6 of them for backstays, if that makes sense. So then now a bridge in my backyard near where I grew up in the woods. So I grew up in the woods on a road job, and so this was quite an interesting moment where we unfortunately had to close this bridge because it was unsafe, and then replace it. And there's nobody up in this part of this between New York and Vermont where I grew up. This bridge was only used by 3,500 people, and I think 3,500 people showed up to the public meetings. Yeah, so there's really nothing going on. And what's interesting is many of the people, my name is the same as my father's and my grandfather's. Many people had worked for my grandfather in the road building days and knew me. And I think they half came just to see what the hell I was talking about. So it was one of the most, I'd say, environmentally sensitive sites of anything I've ever worked on. Pre-Revolutionary War, that's probably a bad topic for this audience, but French and Indian War is a better topic. And then 7,500 years of Native American history. In fact, when the University of Vermont went out, and every shovelful had an actionable artifact on the Vermont side. It was just the entire site was basically a hot spot. So we had to build along the same alignment. And then this is not important. This is a video that so I got very interested in how many cables I could lose, and I'm happy to say that tight-spaced cables you can lose on a network arch. You can lose for 3, maybe 4 cables with still maintaining live load. But the more important thing for me was this idea about construction. And so this was really baking construction into the fundamental characteristics of the design. So on the upper, and this was an emergency project, so we did this design in 10 weeks. So it was really an aggressive design schedule. And you can see that the contractor did exactly, this was not design build, the contractor did exactly what we had come up with. And basically, this is just the use of strand jack, so hopefully this plays. Is that, and just to be clear, this distance is this is a landlocked lake, so I know the lot size, I know the barge size, I know what the geometry has to be, and this is just the lifting of the bridge between two what we call delta frames, and this was the way the bridge was connected. And this, in terms of a strategy, was incredibly effective. And for me, it answered the question of how to build arches without false work. Yeah. So in this case, it's a landlocked lake. You can't get a gigantic crane in to do the lifting. I don't want any false work. The soil conditions are terrible. How do you build an arch where you're using the approach bridges as the lifting device? Yeah. So in this sense, the approaches are the crane. And then for me also, that I really got interested in this distance as related to this to the barge size. So getting into a little bit barge logistics. This is another thing. So now I've done a lot of float-ins. Barge logistics are a good part of this. And then finally, this idea of network arches is really no different than lattice trusses. Yeah. So this is going back to when covered bridges where I'm from are in terrible shape. Usually you can reach your hand in and pull rod out, but they seem to stay up. And part of that is because of this redundancy with lattices. So in the end, I think this was a project that even in a very significant emergency in integrating construction into the design and really trying to figure out how to build arches more effectively is something that I think was fundamental to the way I think about practice. And then, not for nothing, and you get the theme here, is this is another set of arches built around construction equipment. The strategy here was to use and these are, we call these MyJacks. They're basically, gantries like you would use in a fabrication shop, but they're wheeled so they can wheel around. And so this bridge was all designed based on using these yellow things. Yeah, and you can see the temporary support. So the tie girder was designed to support all of this, even the crane and the biggest pick that these gantries had to make was the crane that we needed to erect the arches. You can see that crane in the middle. So this is really the crane has to pick the crane, yeah? And it's a strange way of thinking about design, but I think there's that leverage that can be had in terms of developing new ideas, and that's where the innovation is. And this is just some of the details, but you can see no welding, yeah? We've done a lot of bolted connections. This is still the vestige of the Federal Highway Administration saying you shouldn't be building unsafe network arches. We even used the gantries to take down the old bridge, yeah, and a bit about, there's the picking of the crane, right? So I'm not making that up. Everything was designed around the crane that we needed to pick the arch pieces up into the final configuration. So now a bit about, this is, I think, finding stuff in the backyard sort of approach to bridges. This was another collaboration with men. I don't think he and even Jörg Schleich were completely happy with this. And Jennifer will be, so one of the things I did was I used bent connections as opposed to castings. And so all of these pipes are bent. But actually the more interesting story is that Christian men wanted weathering steel, and weathering steel pipes in the sizes and the strengths that we needed were basically didn't exist. So we started searching around, and the general rule in the United States, if you're looking for steel, look in Western Pennsylvania. Somebody will have stocked some steel in Western Pennsylvania, and I'm not making this up. We found some Japanese steel and Corten steel in Western Pennsylvania, and I took everything he had and said, okay, we're going to design the bridge around what available materials he had. Yeah. So this is, and of course, this is on Princeton's campus, which is very fancy, and that's maybe the proudest I am of this is that this fell off the back of a truck sort of steel, but it's fundamental to the design itself. And then this was a fabricator who had never fabricated with pipes, and he did a fabulous job. And then one of the things that I got scolded, and I like to get scolded from time to time by men and Jörg Schleich, was that the joints, the connections where they had to make this in the field, right? Because these pieces aren't, now you know me, right? This is not over-the-road transportable, so that splice happens. You can support this on a truck, the next piece you can't. So that's where the splice had to be. And I left the splice, I didn't have them clean up the splice. I like to show where the splice happened. Yeah, and that apparently isn't well thought of. The other piece in this for me is that this is pure graphic statics. This is a bridge that only graphic statics makes sense. You've got a widening. If you think about the roadway width, the pedestrian walkway width is widening. It creates different loads. Those different loads create different reactions. The arch shape is not clear. It's clear in graphic statics. So this is an example where graphic statics is the only way to design something like this. There's no other way to figure out the shape of the arch. And so it's also something that's a little bit of a throwback, and I think has a vestige of men and Etihad and early training. So then this is sort of me ripping off things, right? So this is a rip off of what's in covered bridge terminology. This is a town lattice truss and a burr arch. And so for me, this is made out of locust, so you don't need the cover. And this was for Vassar's campus, but this is the same idea. Even this, it's transportation and erection, right? Comes in one truck, can be lifted with one crane and set. Yeah, so that's where the efficiency is. The rest of it is not meaningful. And so I'm coming to the end here. I people have taken my course. They term it the demonization of the truss. So I feel like trusses are failing at 20 times the rate of any other sort of structural system, and I feel like we engineers, if we can have one part, one connection fail and the bridge ends up in the water, we've done something horribly wrong. So when I have to design trusses, it's always in the back of my mind that my students are giving me a hard time. And so I really stretch to try to find a way to make trusses really intrinsically redundant, and by using I shapes in the strong axis was what the idea was. And some of this really goes down to fabrication. So I got very interested in how so this is just using splices as opposed to gusset plates. How to fabricate trusses in a new way that takes full advantage of the material and reduces waste. And in a sense, this is sort of a sustainability thing. Plate comes in slabs, and you can cut Mickey Mouse shapes out these days with plasma cutting. Can I cut shapes and then use the same thicknesses? So this is a bridge, a truss bridge that I think that's just about the welding. That's not very interesting. And the plate bending also not very interesting. Here's the prefabrication. To me, the idea here that you can build a truss this complex, so all three trusses that I'll show you in a second only used 4 plate sizes. Yeah, so this is absolutely not efficient. And the one thing I forgot to say is this is a movable bridge, right? So the one thing that you pay a huge penalty for in movable bridges is weight. And so we were 30%, even though we won this project, we were 30% heavier than any of our competition, and we still won the project. Yeah. So this is a very clear indication that actually less plate sizes is probably more efficient and more sustainable, and certainly more cost effective. So a little bit more, so I laugh now when I think about, arches are not allowed, and it seems like half of what we do these days in the US is arches. So this is a set of concrete arches in the West Coast. We just finished a pedestrian bridge, a sort of odd-shaped pedestrian bridge. I've always wanted to do a skewed arch because I think they look funny, and they do look funny. And this was one where we're moving the bridge over traffic. This is Texas, where traffic never stops. And yet, I think it's a very strange-looking bridge, right? And I guess that's a bridge only a bridge engineer would like, and so yeah. So it is. So then rope bridges, and this was around, Jennifer, your time when we were doing. We had students making bridges. This is out of a cat's cradle idea, and I got the sensibility. Same thing, transportation, fabrication, erection. Why not use synthetic rope? And so this is a bridge in Morocco, done with Engineers Without Borders. That I didn't want to do another one until it lasted 10 years, and it's 11 years old now. So maybe it's time to do another one. So now, and I'm really to the end. So now I'm wondering, so that's slow change, and I'm thinking we're not well adapted. What about all these fast changing things that are happening, particularly with climate change? So what we're seeing all throughout the United States is very high localized amounts of rainfall that are taking out bridges. And, this is the sort of fat tail problem. This bridge in Texas, that was the 250,000 year return period storm. I just think we're nonsensical at this point when we say such things. Yeah, we have a problem, and we are not going to be able to fix the problem, in my view. So part of it is really focusing on rapid restoration. And so I've now done a series of projects, and this is me now. This is on the cultural transmission, or you could say the imitation side of things. I'm completely interested in using filler beams. Yeah, something that you use here, and we are absolutely not allowed to use in the US. And so I have to wait for these emergencies before I get the right to play around without design codes that are recognized. So this is an example of a filler beam bridge we did in New York City. The other problem we're having all over the place is vehicular impact. All we do is have overhead vehicles run into bridges. And this one is actually one we fixed. Yeah, we spent $1 million fixing it, and it tore it. It's just absolutely ridiculous. We fixed it 2 years ago, and I got hit again. And so finally, we were able to enhance the clearance and have a much more robust structure with filler beams. And so the last thing I'm working on, and this is the bolted up stuff, so I got very interested in using workflows from transmission line manufacturing or transmission tower manufacturing. So this is the bridge, not a weld to be found, and all I'm doing is brake press bending plate in Z shapes, like Zoli, things should have Z shapes. But it's that these guys have steel on the ground. No US fabricator has steel in stock. These guys, because they're making transmission poles, have steel on the ground, and my thought was, hey, I can use steel on the ground. I can say, make this piece and then respond more rapidly. And we've done now a few demonstration projects with that technology. So the stuff that makes me nervous, tire pressures are getting heavier. We have significant orthotropic deck problems. Yeah, we're having decks that are only lasting 15 years that have design lives of 100. We see significant problems with changing from duals to super singles, which, as I understand it, you guys developed here, so thanks for that. But it's that we have a design code that has the contact pressure is 40 psi, and we're seeing the steering axle 130 psi. If you look at the way tires are being designed, they're delivering much, much higher loads. And this is my worry, that we don't have codes that can adapt. And the other piece of the problem is we have lawlessness in the US, as you might imagine. The legal limit is here. Yeah, you can see how long the tail is. We have grossly overweight vehicles. And not surprisingly, we have brand new, I say brand new, less than 20-year-old decks with fatigue cracks, all in the truck lane. This is the truck lane. All you do is you see web to deck cracks and floor beam cracks. Yeah, and so I'm worried that every orthotropic deck we build is going to have this problem until we change. And we do all these tests and so on. And then obviously this idea about vessels and, yeah, I mean, if we have a bridge collapse, why would we be surprised, right? And the code's able to adapt quickly enough. And so in the end, I just feel like, so for me, this idea of adaptation has changed inevitable. There's a lot of slow moving change that we're not reacting fast enough to. There's a lot of fast moving change that I'm really concerned about. For me, my career has been on fabrication, transportation, erection. All of the innovative things I've done is in that space, yeah? And that, in my view, is 50 years too late in a sense. And I say this all the time, we're leaving this next generation with much more challenging times, with much more rapid change. And this is where this idea of learning versus, or I would say innovating versus imitating, I'm afraid we haven't given you much to imitate. And we have a lot of learning to do. And I think that logic is really, really important for you to hear, especially you young people. And for me, I think the tail end of my career, I'm really trying to focus on smaller span bridges and the larger problem of being able to rapidly respond to events that we won't be able to address. Yeah. Thank you.